Okay, so today we're going to learn about limits, and limits is pretty much the introduction to any calculus class. It's the groundwork of calculus, of derivatives, integrals, series, Taylor expansions, pretty much everything in calculus, because limits deals is the first time that you'll deal with infinities. And I guess before that scares anyone, we'll just come up with what a limit even is. So the way that I would think about a limit is, so let's say that the limit as x goes to a certain number, what value does this tend towards? So what value does f of x tend towards? So as the input tends towards a certain number, what does the output tend to while it approaches that number? So I think the best way to illustrate this is through just an example. So we'll just make an xy coordinate plane. Yeah, so then if we say that f of x is equal to, let's say 2x, so there's a pretty simple function. It's just something that looks like this here. And let's say that we want to take the limit at 1. Well, so the limit as x goes to 1 of f of x, so we just have to ask ourselves, as the input goes to 1, so as x goes to 1, what does the output tend towards? So if we see here, as x goes towards 1, the output tend towards, we just look at the output now, which is the y-axis, tends towards 2. So we know that the limit here is 2. But now let's do another example. Let's do a graph that looks something like this now. So y, and then x. So we'll use the same function here. I won't redraw the numbers, but you get the point. It's we'll just do 1 again, and then 2. So before there was something here, but now let's say that we erase this point here, and then we fill it in now with a hole. So with, so then with this hole, there is nothing at this point. And this hole only exists at the point, so now this function is f of x is equal to, it's a piecewise function now, so it's 2x. When x is not equal to 1, but it is, it's just 2x when x is not equal to 1. And then whenever x is equal to 1, there is just nothing. We just assume there's nothing there. So then now we just have to ask ourselves, what number still, the limit as x goes to 1, what does the output tend towards, right? So then we do the same thing. We think about, as x goes to 1, what does the output tend towards? We don't ask ourselves, what is the output? What is the value of the output? We just ask ourselves, what does it tend towards? So let's say that we get to 0.999999999, repeating. We, as x is getting closer and closer to 1, it's getting closer and closer to 2. But x never actually reaches 1. That's why we say it's the limit as x approaches 1. If we want to actually reach 1, then all we would do is just do f of 1. We just put x is equal to 1, and of course there's nothing there, so it doesn't exist. But for the limit, it's a different switch in mentality. So in this case, the limit as x approaches to 1 of f of x will actually just be 2 again. Yeah, so there's nothing that actually changed. Okay, we'll do another example. Oh, actually, before I go, this is called a jump discontinuity. And what this means is that, oh, sorry, not jump. This is a removable discontinuity because it's almost as if someone just removed one point from it, but the entire line is the same. So that means that if you add back that point that you removed, then it becomes a continuous function again. So if we filled in this hole, then it's a continuous function. So yeah, removable discontinuity. And this function here is a fully continuous function, the one that we wrote before. So that means that the limit is defined for every x value. And yeah, what a continuous versus a discontinuous function is a discontinuous function, you would have to lift your pen to draw the function. So remember there was a hole here. So that means if we were to try to draw it out, we would have to lift our pen and then put it and try to draw it again. Okay, so we'll do another function that further explores limits. Okay, so then now what happens if we define a function that looks like this? Yeah, so then it jumps here. So this function is f of x is equal to, it's equal to 2x for when x is less than or equal to 1, and it becomes 2x plus 2 when x is greater than 1. So this means that it's the same function as before for 1 or less. So as x is 1 or less, it's the same function that we had before in these last two examples. But now, whenever x is greater than 1, it's the same function, but shifted up 2. So let's say that this was 2, so that's what it was before, but then now this is 4, right? Because, if you just plug in the numbers, that's what you get. So then, now, if we do the limit again, what do we get? So this is now when we have to come up with a better definition for a limit. And so the limit at this point, the better definition for it is that the limit as x approaches a certain number for f of x has to be equal to the limit as x approaches that number from the left, which is why there's a negative there, and f of x, and the limit as x plus approaches that number f of x. Yeah. So all three of these things have to be equal for the whole limit to be true. So this negative just means what does the f of the output tend to as x approaches that number from the left, while the plus means what does it f of x approach when x comes in from the right. So if we look at this case, so as x approaches from the left, we see that it approaches a value of 2, right? Which is like somewhere here. So 2. But then when x approaches from the right, we see that it approaches a value of 4 instead. So if we fill in a blank, then this is 4, this is 2. So that means that these are not equal to each other, right? So then the limit here does not exist. And this is called a jump discontinuity. So jump. Okay, I won't write this discontinuity, but yeah, jump discontinuity. This is because the function jumps. And it's discontinuous because you have to lift your pen, but at the same time it's jump because the limit doesn't exist, because the whole limit doesn't exist, even though the left and right one exists. So yeah. And another thing that I want to clarify is, let's say that for this one, right, for the removable discontinuity, there's a hole here, right? There's nothing here. But then you add another dot here. Does this mean that the limit changes at all? No, the limit doesn't change. It's still 2 for this function. Adding this just means that the function is defined for x is equal to 1. Before, the function was not defined. So for example, if I ask you, what does f of 1 equal? Before I added this dot here, it does not exist because there was no point here for x is equal to 1. But after I added this dot here, it's no longer does not equal. It's whatever this value is. Let's say it's 4, right? So then now it's 4. And the same thing goes here. If this function is actually defined at x is equal to 1, because I said less than or equal to 1. So even if it's defined at x is equal to 1, it doesn't mean that the limit exists. This is what has to be true for the limit to exist. Okay, so we just went over a lot of examples of what can occur with limits, but we'll do one more example that shows the full picture of what can happen with limits. Okay, so then I'll make a coordinate system real quick. Okay, so let's say I define a function f of x is equal to sine 5x minus 1 for when x is less than 1, and then we'll say that x is equal to 1 whenever x is equal to 1. No, sorry, f of x is equal to 1. I will just do 2, it doesn't matter. And then we'll do 1 over x minus 1 for when x is greater than 1. So this is the example that Wikipedia had on their page. So then we'll just draw out the functions real quick. We'll draw out the sine one. So sine one looks something like this, but then it gets like this as it approaches. This is so bad. It looks like this, but then it just like gets closer and closer as it approaches 0, and it just keeps going like this. But if you can tell, as x approaches 0, oh shoot, it should be 1. It should go all the way to 1 like this. So it just keep going back and back and back like this until it hits 1. X is equal to 1. And the reason why this happens is because as x approaches 1, the denominator here gets smaller and smaller, right? And as this denominator gets smaller and smaller, the entire value inside these parentheses here gets bigger and bigger. Because let's say you divide 5 by 0.1, that's 50. And if you divide 5 by 0.01, that's greater than 50. And the closer and closer it gets to x, the greater and greater this thing inside the parentheses grows, the faster and faster. And the reason why it wiggles faster and faster as it goes to 1 is because sine makes it where it's just like a unit circle spinning back and forth like this. And the thing inside is the angle. So that means that the angle is changing faster and faster and faster. And then we're just taking the value of the y. And that's what this amplitude represents, the value of y. So yeah, but if you think about it, as x goes to 1, does this ever approach a certain value? It never approaches a value. So that means that the limit, I should do it in red, since I drew the function in red. The limit as x approaches 1 from the left side does not exist. Okay, so we already know for a fact that the limit of this entire function doesn't exist because one side doesn't exist. It just doesn't even go to a value. Okay, so then now we'll think about what the value of f of x is at 1. It's just 2. Let's just say 2 is somewhere here. I don't know actually where it is relative to this function. We'll just say it is. Yeah, we'll say 1 is here. X is equal to 1 is here. But then this doesn't really matter because we saw from the previous examples, even if the function is defined at a point, but the left and right limits don't exist, then the whole limit doesn't exist. And then now we'll draw this function. So yeah, so then it will look something like this. And this is the last thing about limits that if you know, then you pretty much can do any limit problem. So then now we, let's say we write the limit as x comes to the right and approaches 1. And then we ask ourselves, what does f of x approach? So what does this function approach? So, or y, since y is f of x. So y approaches, right, if it comes in from the right, it approaches infinity. Because, yeah, just y just keeps going straight, right? And the reason why that happens is because the same thing here. As x approaches 1, this denominator value will get smaller and smaller. But because it's in the denominator, 1 divided by, let's say, 0.1 is 10. And then 1 divided by 0.01 is greater than 10, et cetera, et cetera. We'll keep going. So yeah, it approaches infinity here. So infinity is an abstract, I guess, concept. And it still exists just because we're talking about what value does the function approach, not what it actually is. And this here is called an essential essential continuity. So we see that the limit from the left and the limit from the right doesn't exist. So we know for sure that the limit as x approaches 1 of f of x does not exist. And it's an essential discontinuity because the limit of either the left or the right side tends to a value that is not in the set of real numbers. And this is the symbol for the set of real numbers. Does not exist is obviously not in the set of real numbers, and infinity is also not in the set of real numbers, even though it's not as obvious, because infinity is just a concept. It's not a number in itself. Okay, another last thing I want to talk about is what does the limit look like as x approaches infinity now. So what does this function, what does the output approach? So what y value does it approach when x goes all the way to infinity? So if you could see, it actually does tend to a value, and this value is 0. Will it ever get to 0? That's a topic for a later discussion, but limits is about what does it approach, and y approaches 0 as x goes to infinity. And the reason this is because if you imagine what happens when x goes to a very large number, the denominator gets smaller and smaller, right? The denominator gets bigger and bigger, but the 1 over this bigger and bigger value gets smaller and smaller. So 1 over 1 million is essentially 0. So if we go 1 to 1 trillion, or 1 over infinity, that's essentially 0. So yeah, that is an introduction to limits. We learned about removable discontinuity, jump discontinuity, and essential discontinuity. All right, thank you.